Allah Ta'ala wabarakatuh and salam sejahtera. Okay, today we will discuss on chapter 6 for benzene and its derivative. Okay, there are three parts or three subtopics we will discuss in benzene and its derivative. One is 6.1 for introduction, 6.2 for nomenclature of benzene and its derivative, and 6.3 is for chemical properties of benzene. Okay, for lecture we will discuss only for 6.1 and 6.2, whereas 6.3 we will discuss on our tutorial classes. Okay, for 6.1 we will describe what is aromaticity. The second one is what is a Kekuli structure, and the third one is a resonance structure of benzene. Okay. Okay. Actually, the word aromatic came from the pleasant odor. Okay. This the pleasant odor of the compound. In early discovery of benzene. That's why the scientists at that time called benzene structure as a aromatic structure, because of this their pleasant odors. Okay, but for today we use aromatic, or aromatic compound specifically to benzene and the structure, and structure that related to the benzene. Okay. Okay, so for benzene, okay, we can classify as an arene, okay, because arene is a one type of hydrocarbon. If okay, if there is no other atoms attached to the benzene ring, for example, benzene itself, okay, naphthalene, and also this structure is a toluene. Okay, so if there is no other compound beside carbon and hydrogen, so we call it as a arene. Okay, that's why arene is called as a aromatic hydrocarbons. Okay, and the benzene is the simplest aromatic hydrocarbon. Okay, so what is aromaticity? Okay, okay, so there is a for a compound or for a structure that we can consider as aromaticity if that a particular structure comply with these four structural criteria. Okay, so if this structure is fulfill all these criteria, we can call it as a aromatic compound, either aromatic hydrocarbon or aromatic or other organic aromatic. Okay, the first one is cyclic. So the structure must be cyclic, planar, completely conjugated, and the last one is obey to the Huckel's rule. So I will discuss all these four types of criteria for aromaticity. Okay, the first one is cyclic. Okay, cyclic means the structure must be close chain. We call it as a close chain. Okay, that is the difference between cyclic and no cyclic. We call it as a acyclic. This one is non-cyclic. Okay, non-cyclic or acyclic. Okay, so in order to exist as a benzene or aromatic, okay, the structure must be cyclic. Which is every p orbitals overlap with their neighboring p orbitals. Okay, their neighboring carbon p orbitals, and this one is aromatic. For this one, for example, 1,3,5 hexatriene is a acyclic or non-cyclic compound because there is no connection or no connection between these two p orbitals. So we call it as a non-aromatic. Okay, to be aromatic, each carbon must be with the adjacent. Adjacent mean side by side atoms. Okay, that is the first criteria. The second criteria is a planar. Okay, okay. Uh, it must be planar. All adjacent P. Adjacent is side by side or neighboring atom. All adjacent uh, P orbital must be aligned so that the pi electron density can be localized. In another words, planar, the hybrid must be sp2 lah. Okay. Okay, so that was the second criteria. The third criteria is completely conjugated. Okay, what do you mean by completely conjugated? Okay, completely conjugated aromatic compound must have a okay, this one completely conjugated. Okay, benzene as a p orbital of every carbon atom. That means each of these 6 carbon atom, each of the 6 carbon atom must be have a p orbitals. Okay, for 1, 2, so 1, 2 cyclohexadiene and also 135 cycloheptatriene is we cannot consider as an aromatic hydrocarbon, so aromatic benzene because there is no p orbital at the adjacent atom. Eh? Okay, so that was the third what we call it criteria to become or to exist as a aromatic. And the last one is satisfy the Hacker's rule. So in Hacker's rule, okay, the structure is we can consider as an obey to the Hacker's rule when there is we determine the number for n. Okay, for n. N should be n should be okay, should be either 0, 1, 2, 3 and so forth lah. Okay, for example, this structure, okay, 6 pi electron, we calculate this one, 1, 2, 3, 4, 5, 6. Okay, 6. So the formula is 4n plus 2 is equal to 6. Okay, 6. So n will equal to 1. So this structure is we consider obey to the Hacker's rule. Okay, if the number of n we got 0.5 or not the exact number, okay, so that one is not satisfied to the Hacker's rule. Okay, okay, let determine either all the structure is uh, aromaticity or not. Okay, the first one, the criteria should be cyclic. Okay, so this structure is comply. This one is cyclic. Okay. Okay, then this the second criteria is a planar. So this structure is a planar. Okay. The third one is completely conjugated. Okay. Actually, this structure is not completely conjugated, but to make sure that this structure is positively is not an aromatic, we can check the Hacker's rule. The Hacker's rule is for n plus 2 even to pi. We have 1, 2, 3, 4, 4 pi. So for n plus 2 is equal to 4. Okay, for n is equal to 2, so n equal to half. So this one is not obey to Hacker's rule. Okay, so that's why we cannot consider this structure is a aromaticity. So and you can try for all this structure. Most of the structure is cyclic. All the structure is cyclic, but the most important thing is to check the Hacker's rule. Okay. Now we go to the second part in introduction. Is a Kekulé structure of benzene. Actually, Kekulé is a name of one scientist, Auguste Kekulé, who proposed a cyclic structure for benzene. Okay, so in the calculus structure of benzene can be written as the 6 member of rings. Okay, because the structure itself, the molecular formula for benzene is C6H6X, so that's why the calculus structure for benzene can be written as the 6 member of rings atom with alternating singles and double bonds. Okay, and one hydrogen atom is attached to each of the carbon atom. So this one is, we call it as a calculus structure, 6 members, cyclic, and the single and double bond is alternate between these 6 members. So we can write like this one for expanded structure, or this one, we call it as a skeletal structure. Okay. Okay. And the last part is we will discuss on the resonance structure. Okay, each carbon atom in benzene is a sp2 hybrid. Okay, that's why benzene exists as a planar structure. Okay, these 6 2p orbital overlap from to form 3 delocalized pi bond. As we can see here, okay, there are three pi orbital, and which will form the double bond on this one, and as a result the resonance structure of benzene is a hybrid resonance from two calculus structure as shown below. So for benzene we can write like this one, or we can draw like this one. This one represent these two structure, because of the resonance structure exists in the